we've begun. So, emission and absorption spectra are a phenomenon which is related specifically to elements. Just using my high-tech showing of these things. I'll put a doc together a bit later which has got that in. So every element has its own emission spectrum. What I've got here at the very top is the emission of white light from some emitter which emits white light. So for example, an incandescent bulb. If instead of having an incandescent bulb we have a tube that has a single element in it, the colour will be unique. And those little lines are very, very narrow bands of wavelength that that particular atom is creating. So if we have a look, we can see that sodium has got those bands, hydrogen in fact has got those four colours. So it's got a red band. They call that light blue, but to me I'd call that greeny blue. A dark blue, a violet, and sometimes you can see a fifth one which is another violet right next to it. And as you have a look at the other ones, cesium's got much more, magnesium, so on. Neon is when you actually look at neon as a glowing tube, which we'll do when you guys get back, it's a very orange looking look and it's very heavy, much more at the orange yellow end and not very much down here, so it gives it quite an orange glow. Hydrogen has more of a sort of a rosy glow where these colours down here dominate. Those are emission spectra. We also have absorption spectra, and so what happens with an absorption spectrum is simply the reverse. So the sodium absorption spectrum, here's the sodium emission spectrum. It only creates those two lines, which are sort of a yellow colour. With an absorption spectrum, what you do is you hit the atom with white light and it absorbs those two wavelengths and just basically leaves a gap. The hydrogen emission spectrum is kind of annoying actually. I thought the picture would be better than that, but we're stuck with it now because I want to keep going. It would look like an ordinary full spectrum, but there would be gaps. There would be a gap for the red, there would be a gap for the blue-green, there would be a gap for the dark blue, there would be a gap for the violet, and if we were able to see the fifth one, then there would be a gap for that too. There are actually more up here where they head on into the ultraviolet, so we can't see those. Okay, so what is the connection for to Bohr's atom? Clearly, there has to be a connection to an atom. If every element has one, then it must be a connection to the atom. And what's more, the one that every element has is unique to that element. So every element has one that is unique. To that element. You'll have to forgive the fact that I'm doing this one-handed. I thought this time last year, well, when we were in lockdown last year, I stole a clamp stand and put my phone on it. This year I must have taken the clamp stand back. I think I must have had it for about, I've probably only taken it back 2 or 3 months ago. Alright, so what does Bohr say? Well, Bohr says Bohr says two things. The first of those things is that the electron has stable energy levels. Now, he was only able to get a mathematical one for hydrogen. What he found was that every other element was too complicated. It does lead on. It can be applied to other elements as well, but mathematically he had a model for hydrogen. Okay, and so the nth energy levels, energy was equal to negative HCr all over n squared. And E1 equals the ground state. It is the closest that the electron can come to the atom, the nucleus. So let's put the nucleus. The nucleus for a hydrogen atom is just a proton. So we have E equals 1 here. We have E equals 2. E equals 3. And what we actually, it's hard for me to draw this for a variety of reasons, not least of which is my paper's moving, is that, let's do 2 more. So that's E equals 4. And we'll do 1 more after that. They're certainly not a circular thing. In fact, what they are is a sort of a probability function. Alright, so what he said was that they have all those energy levels and they're all equal to E equals negative HCr all over n squared. How that works then is that if En is equal to 0, then the electron is off the atom. The atom has been ionized. E1 has the largest numerical value, but it's actually the least negative. Sorry, start again. It is the most negative, which makes it the lowest. So E1 equals most negative, so it equals lowest. And what that value actually represents is the amount of energy that you have to put in to that particular hydrogen atom to get the electron out to 0, or out to infinity, in fact. So E infinity is equal to 0 because negative HCr squared, HCr all over n squared is equal to negative HCr all over infinity, and when you divide by infinity, that's 0. Right, so n equals 1, most negative, so it's the lowest. N equals 2, the next lowest, so it's actually a higher energy level. N equals 3, the next lowest, so it's a higher energy level again. So as you head out, those energy levels are less and less negative, which makes them higher and higher. Now, that's how that works. So the electron's status and explaining all of that was all about ascribing this negative energy status, and it's telling us about the amount of energy that's required to get the electron from energy level 1 out to infinity, electron from energy level 2 out to infinity, etc. The second thing that Bohr said is if the atom absorbs the correct amount of energy, before we go there, the other thing that Bohr said in regard to energy levels is the electron cannot be in between. It can't be at E equals 1.5 or 1.75 or 1.875. It can't be at any of those places. It has to be at 1, or it has to be at 2, or it has to be at 3, or it has to be at 4, or 5, or 6, or 7, or 8, all the way through to infinity. Can't be in between. That's an interesting thing, because that implies that for it to jump from 1 to 2 must be almost like a beam me up Scotty deal going on there. Somehow it's able to simply jump from one to another without actually being present in between. Right. Second, if we have the electron, start again, no, second is that if the atom absorbs energy of the precise difference between E equals N and E equals some other N, the electron will jump there. Okay, now that can be done by absorbing a photon of exactly that value. So if a photon of E a photon is actually is 100% equal to E final minus E initial, electron will jump. And the photon will be absorbed. So let's say that we've got an electron out at number 2. And it absorbs a photon whose energy is exactly equal to the difference between E2 and E3. It will jump up there. It just so happens that that is equal to the energy of the red line for the absorption spectrum for hydrogen. If it was a bigger one and it jumped all the way from 2 till 4, then it will absorb a photon of blue-green. So the blue-green line. If it goes all the way to from E2 to E5, 3, 4, 5, it will absorb the energy of blue, the blue line. It creates the blue line. If it goes through to the next one up, it absorbs energy of violet. So this is how the absorption spectrum for hydrogen is created. So let's go back. It's the reverse of that. Okay, so we'll get on to how this one is done in a minute, but the reverse of that is the electrons are forced to jump out because they are absorbing photons whose energy is exactly equal to the difference between E2 and whatever's next. So E2 to 3 creates the red, the black bit that where the red should be. All those reds are absorbed. The blues are absorbed, the blue-greens are absorbed by having the energy being sufficient to go from 2 to 4. The dark blues are absorbed by having photons whose energy is exactly equal to E2 to E5. The violets are absorbed by having photons absorbed whose energy is exactly equal from E2 to E6. So it's just a mathematical thing, it's this. Now we don't provide you with that, but it's straight addition, or it's subtraction in fact. We don't provide you, it's that there. We don't provide you with that. We expect you to be able to know that this is kind of like changing. And so that's where we've ended up, and that's where we've gone. You'll just have to be a little careful when it comes to dealing with negative numbers and subtractions and stuff. What you really want is just the absolute difference. Now, let's go the other way. So let's say an electron is out at red. So it's out at 3. If it drops into 2, if there's something about the atom has been kept in an excited state, and I've got a transformer that will do that. It's got 15,000 kilovolts. It will emit photons of red. It will emit those. If an electron drops from 4 to 2, it will emit blue-green. It will emit those. If it drops from 5 to 2, it will emit blue. It will create that line. If they drop from 6 to 2, they will create violet. Okay, so, and that is your emission spectrum. So what happens to create that emission spectrum is that you have the atom. They describe it as excited. So energy is going in, which could be that it's in a hot place, like in the middle of a star. Could be that in the case of my emission, my spectral tubes, I put a big voltage across it. Now, while we're still here, that leaves us with, instead of, so dropping to 2 or rising from 2 gives us the spectrum, which is visible. If we were going from 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, that gives us a UV spectrum. Now the name of the visible spectrum is the Bohr series, and the spectrum's number is 2. The spectrum's number is 1. This is called the Lyman series. Now, if we went from 3, 1, 2, 3. So 3 out to 4, 3 out to 5, 3 out to 6, 3 out to 7. This creates an infrared series. Now the name of that series is the Passion series. Okay, and so the series number is 3. Now the reason that I'm alerting you to S1, S2, S3 is that ties in with Rydberg's formula. So Rydberg's formula, let me just finish this statement here. So if a photon is absorbed, it will jump. If an electron drops from E initial to E final where it's dropping in, then delta E is equal to the energy of the photon, and this creates our spectral emission lines. Emission means to emit, so these are lines coming out. Absorb means to absorb. That's a surprising thing. And that means that these are colours that are being absorbed by the atom, and they give us these black bits up here. There, those black bits where photons of those colours are being absorbed. There are some more down here. these ones here, the only colours that are coming out are these ones being emitted. The only ones coming out are these ones being emitted. Right. So that leaves us with Rydberg's formula, which is 1 over lambda is equal to R into 1 over S minus squared minus 1 over L squared. And so S is equal to the series number. So S equals 2 for visible, which is Balmer. S equals, S equals 1 for UV, which is Lyman. S equals 3 for infrared, which is Passion. 4 and 5 are also infrared, and so it goes on. So that's how the series number, that'll go in there. The L number, what you do is you have L equals S plus 1, S plus 2, S plus 3, S plus 4. So that actually means that S is the number it's come out from, and S plus 1 has gone to 3. So that's the first line is the red, it's gone to 3. The second line is the green blue, it's gone to 4. The third line is the blue, it's gone to 5. The fourth line is the violet, it's gone to 6. So 2 plus 4 makes 6, 2 plus 3 makes 5. That's how that works. So 1 over lambda for red is going to be R into 1 over 2 squared minus 1 over 3 squared, and whatever that comes out to. You'll find that will work. Now, that's